Okay, folks, we're going to now look at projectiles. We're going to combine what we know about free fall that we've been doing, that we did before the last test, and the vectors that we were doing before the last test. And we're going to combine those together, both the x and the y directions, and we're going to look at how a projectile works. So we're going to start off with reviewing 1D projectiles real quick. Remember, if we drop something, we say that the initial velocity is 0, and that the v final is not equal to 0. It's going to be something larger, and it'll be negative, but it'll be larger, right? Because it'll be acting downwards. Right? What does a marble look like when I drop it? Right? If I were to just draw kind of a time-lapse photo, here's the beginning, here's the beginning right here. Then after a short amount of time, it's gone this far. Same amount of time, it's going even farther. Same amount of time, it's going to go even farther. It's going to get farther and farther and farther apart for every second or half second or whatever that goes by. Right, so when the marble is dropped, what's the initial? Then we said the initial vertical velocity is 0. VIY is 0. Right? If I drop the marble from 1 meter tall, how long will it take the marble before it hits the ground? So we write our knowns, right? These are our givens. So we write this in our givens box. VI is equal to 0. DI is -1. Acceleration is -9.8, and my time is my question mark. Remember, my dy is -1 because it's going downwards. Right? So if we look at those equations, we look at our kinematic equations, this is the one we're going to use. dy equals vit plus 1/2 at squared. This is 0, so it basically is just 1/2 at squared. Right, so -1 is equal to 1/2 times -9.8 times t squared. So -1 equals -4.9 t squared. Then we divide both sides by -4.9, and we take the square root. So our time it takes to fall is 0.452 seconds. All right, we're going to use the same equation. We're going to work the same thing when we do projectiles as well, because we're going to need to know how long it takes for it to hit the ground. So this is just a review, but we're going to use it again. All right. And then what's the vertical velocity when the marble hits the ground? Again, we write down what we know. Right? These are the same things that were given before. Right? And we calculated t, and now we're looking for VF. Right? So which equation are we going to use to find VF? I would use VI plus AT. VF equals VI plus AT. That's 0. That's -9.8, and we know the time. When we do that, we get -4.43 meters per second, meaning it's going downwards. Right? If you wanted to use the other equation, we could use VF squared equals VI squared plus 2AD. Same values. We end up getting, amazingly enough, the same answer. So either way is perfectly fine. Right? This drop marble, does this drop marble have velocity in the horizontal direction? No, because it goes straight down. Right? Vx is equal to 0. We're going to have to combine those two things now, because a projectile is not going to have a Vx equal to 0 most of the time. Right? So a projectile is an object in the air under the influence of gravity only. So basically, it's an object under free fall is a projectile. Right? Dropped and thrown objects can be considered projectiles, but typically thrown things. All right, I want you to think about this statement here. This is an important concept that goes along with what we're going to do here. Right, so if I have a marble that is launched horizontally, that is due straight to the right, right, at the same time, a marble is just dropped and allowed to go straight down. Right, just dropped, not thrown downwards, but just dropped. All right, which marble will hit the ground first? Right, and that is a trick question, right, because they're going to hit the ground at the same time. If that doesn't make sense to you right now, we're going to do a lab tomorrow that you should be able to see how that works. Right? And if you're not sure about that, still check with me on Monday and we can talk about it some more. All right, so What's important when you're working with projectiles is that you must look at the vertical and the horizontal components independently. You look at them separately. Nothing about the X motion affects the Y motion. Nothing about the Y motion affects the X motion. Right? So if an object takes 5 seconds to fall, right, if I drop a dropped object, if it takes 5 seconds to fall, how long will it take if I launch the same ball horizontally at 1 meter per second? So I just launch it this way. Okay, won't it still take 5 seconds? What if I launch it at 10 meters per second? Still going to be 5. What if I launch it really fast at 100 meters per second? It's still going to take 5 seconds to hit the ground. It doesn't matter how fast something moves this way. If it's launched horizontally, it's just the time it takes to hit the ground is just like I drop it. No different. Right, so let's look at those components. Right, so what's the only force that's acting on a projectile? Right, the only thing that's pulling down on it is gravity, right? Right. And which direction does that affect? Does that affect the X direction or the Y direction? The vertical Y direction, right? So which direction has acceleration? The Y. That means the X direction means it's constant velocity, which is really easy to work with. So let's see this works with. The horizontal motion is constant. The vertical velocity increases as it goes downwards. Right? So if we see initially my velocity in the X direction is 5, like it shows here, and my initial Y velocity is 0. But as it continues, it starts moving more and more faster in the Y direction and just moves the same in the X. So the resultant vector is going to increase, which means it speeds up. All right, so horizontally launched projectile leaves with a velocity of 5 meters per second. Right? What happens to that horizontal velocity after 1 second has passed? Nothing. It's still 5 meters per second. How about after 5 seconds has passed? It's still 5 meters per second. Right? What's the velocity, the horizontal velocity at any point while it's in the air? It's 5 meters per second. It never, ever changes. What happens to the vertical velocity as it travels? Right? It goes faster and faster and faster because gravity's pulling down on it. All right, so let's do the math now with 2D projectiles. All right, components again. All right, remember that the horizontal and vertical are independent, and we should look at them separately. And that gravity only affects the vertical component of the velocity. All right, so important variables to know. Horizontally, you're going to want to know dx, vx, and t. You need to know 2 to find the other. And the vertical, just like in all of our acceleration equations, we have d, vi, vf, t, and of course our acceleration, which here is g, negative 9.8. All right, so here's our important equations that we're going to use when we're dealing with this. And of course, we always assume that there's no air resistance. So in the x direction, there's one equation, dx equals vx times time. That's all there is. In the y direction, we have our big 3, the ones we use all the time. Right? dy equals vit plus 1 half at squared, in this case g. vf squared equals vi squared plus 2g times d. And vf equals vi plus gt, or at. So there we go. Same equations that we use. Right? These, notice that only the vertical equations involve g. Right? So what does a horizontally launched marble look like? So if you remember when we dropped it, remember how we said after a second went by, it fell just a little bit, and then the next second went by, it fell a lot farther? Well, same thing's happening here, except it's also moving to the right at a constant speed. Right, there's another example kind of it where as time goes on, you see how it dropped farther and farther, but notice how if you compare it to a dropped one, they're at the same level each time. All right, so how do we solve these problems? All right, we're going to make ourselves a givens box, but this time we have to break it up into x and y. So we're going to write our givens in x and our unknowns in x, our givens in y, our unknowns in y, and then we're going to solve. But we keep the x and the y separate from one another. All right, so a marble is launched at a height of 1 meter and leaves with horizontal velocity 3 meters per second. How long is it in the air? Okay, so what do we know in the x direction? This 3 meters per second is horizontal velocity, so we're going to write Vx is equal to 3. All right, we don't know anything else, though. Right, so we don't have enough information to solve anything in the x direction. But in the y, we know that it's launched from a height of 1 meter, so it's going to fall 1 meter, so negative 1 meter is my dy. We know my acceleration is negative 9.8, and we know that our initial y velocity is 0. Right, so we have enough information to solve for time, because that's what we're looking for here, using my y information. Right? I don't have enough information. The only equation I have for the x direction is delta x equals Vx times t. Well, not delta x. Sorry, let's do that over again. Dx is equal to Vx times t. Right? And I know Vx, but in order to find time, I'd also need to know dx, and I don't know that. Right? But I do have enough information horizontally, so I'm not going to use that yet. Right? I can use dy equals vit plus 1 half at squared. Again, that first part, 0. So it's 1 half at squared. Right? And this is the same problem that we did earlier. Right? Negative 1 is equal to negative 4.9 t squared. And we went and we solved for t and got 0.452 seconds. Hope you remember that from before. Right, so how far horizontally will the marble travel before it hits? So that's going to be, we're looking now for dx. And so again, we have our boxes, right? So now we've got everything we need in the y direction. Now we need dx. We know vx and we know time. So we just say dx is equal to vx times t. So 3 times that is 1.36 meters. That's how far it traveled in the x direction. All right. Now, the last thing that we have to do sometimes is figure out what the final velocity is. What speed, how fast is it going? You know, it's launched this way and it comes down and hits the ground kind of going like this. How fast is it going when it hits the ground? Well, we know it's got x velocity and y velocity, so it's just a matter of adding our vectors together using the Pythagorean theorem like we learned before. All right, so we want to find the vertical velocity. We've already done this, right? Again, we know all of this information. We can use any of our equations. We can use Vf equals Vi plus At, and we get negative 4.43 meters per second. Or we can use that other one. We got the same one either way, right? And so that would be my final vertical velocity. That's my Vfy. Vfy is negative 4.43. But what's my final velocity, right? Well, we know it's moving at 3 meters per second to horizontally, 4.43 meters per second downwards. And so we just use the Pythagorean theorem to calculate that final velocity. V squared is equal to 3 squared plus 4.43 squared. It comes out to be 5.35 meters per second is the final speed as it hits the ground. All right, so work through this tomorrow. You're going to do a lab in which you're going to be hitting golf balls horizontally off of a hill, and you're going to look at things about like the time, and you're actually going to calculate how hard you have to hit something in order to make a hole in one. Right, so you're going to figure that out and kind of do the same process that you did here, and then you also, after you finish with this, then I want you to look at a couple of the problems that are also attached in your e-class site, and we'll go over some of those problems on Monday when I get back. All right, you'll have a great weekend. Finish this up, and I'll see you all on Monday. Bye-bye.